Hi, I'm Van Jacobson from Packet Design. I am giving this talk on behalf of Bruce Ma and Haobo Yu, who did the actual work. And although I've talked at NANOG several times before, usually I have to be drunk to give a talk. This time I forgot to get the key to the minibar, so I'm sober, and I apologize for that. The basis of this talk started about 5 years ago when we first formed Packet Design. A few weeks after we started the company, Randy Bush came by to chat, and we told him all these wonderful things we were going to do for traffic management and controlling IP networks. And he basically said that we were stupid, that he didn't have any trouble controlling the traffic in an IP network. Once he knew where it was, he could make it go exactly where he wanted it to go, but he didn't know where it was. He couldn't see where the bits were in his network, and it was really hard to control something that you couldn't see. And he suggested that if we actually wanted to do something useful, we should go out and make a system that would let you see the bits inside a network, and then people would be able to control it. So it's now 5 years later. It's getting to the point where you can actually do that. One reason it took so long is that we're slow. Another reason is the technology wasn't really there. Up until just roughly the last year, turning on NetFlow in your router was the equivalent of turning off your router. It would slow down to a crawl, and so you weren't likely to get a lot of traffic data. Even if you were getting the NetFlow data out of the router, there was nothing that could sync it. You're getting gigabytes of data, terabytes from an ISP, and you didn't have enough disk space or enough processor power to crunch it. That's all changed, right? Disks are pennies a gigabyte. The processors running 3 gigahertz, you can easily crunch the data. And at least today, ISPs are starting to routinely get flow data. Kind of the current state of the art, what you do with that data is you turn it into a traffic matrix. And while there used to be, say, whole teams at UUNet that would take the data from the previous month and turn it into a traffic matrix so they could do traffic planning, now you don't do anything. You hook up a box, it sniffs your BGP, it grabs the NetFlow data, and based on what it finds in the BGP, it knows how to build a traffic matrix out of that NetFlow data. And things are kind of mature enough so that you don't need to roll your own on this anymore. You can actually buy boxes that do this off the shelf. So here's a traffic matrix. It was generated automatically by a set of data from CNIC, which is the California Educational Network. It handles all of the UC campuses, all of the California State University system, and all of the K through 12 system. It's actually 3 overlaid networks with about 10 million users, and they're kind enough to give us a large set of data and to beta test a lot of buggy code for us. Anyway, you see down the side some of their customers. That was the top 4, which account for about 40% of the traffic, 40% of the transit traffic. Going across the top, you see their 4 transits, and the boxes is a breakdown of the traffic from that customer to that particular transit peer. This is computed off of 24 hours of their NetFlow and BGP data. It's a great tool, gives you a picture of things that are important to your operations, but it's primarily an engineering tool. It can tell you where your traffic comes in at the customer level, where it goes out at the transit level. But if you've got some link in the center of your network that's filled to overflowing, you don't know why it's overflowing, and a traffic matrix won't tell you. All it tells you is what's coming in at a particular customer, what's going out at a particular transit. Its view of the world is just that perimeter. And for a lot of operational questions, you need a different view. And similarly for business questions, if some VP comes down and says, why are we spending umpteen megabucks a month on that transit? Can you prove to me that they're the best? If somebody comes in with a lower price, can you tell me why I can't move to the person that's got a lower price? Well, that's not a question you can answer from a traffic matrix either. It doesn't have a view beyond your borders. It only tells you a little bit about the perimeter. One reason that you start with a traffic matrix, which again is a wonderful thing. I'm not saying you don't need a traffic matrix. It's just you need a lot more stuff in addition. But a traffic matrix is, in a sense, the simplest analysis that you can do of the traffic data. It's only n squared, where the n is just your perimeters, the number of customers plus the number of transits. And that's a relatively small number for an ISP. If you want to do, why is this damn link so full, you need to do at least an order n cubed analysis. What you need is for every pair of routers in your network, for the traffic between that pair at every other router, you need to know how much the traffic between that pair goes through that other router. So that's a router cross router cross router, an order n cubed analysis. And that's, typical network, a couple hundred routers, that's a big number. You're up in the millions now. And if you want to answer the business questions about, well, what am I really using that transit for? That's a path analysis. All path analyses are combinatorial because the data can go lots of different ways. Combinatorial means factorial. And the n in a path analysis is the number of ASs in the internet. So you're talking of numbers that are like 10,000 factorial. And now we're talking about numbers that are like bigger than the universe. So it's not the kind of analysis you're likely to do. And because of that, conventional wisdom says, hey, traffic matrix is the best you're going to get because all of these other analyses are just way, way too hard. But that's wrong. The scaling numbers are derived from all of the places where the data could go. And the network's fully connected and it heals itself, it reroutes. That means that there's lots of different paths. And if you're answering any particular question, any fixed question, then you have to account for all of the different ways that data could go, and that gives you a huge scaling number. But if you actually follow the bits for a little bit, you find that they're usually routed over shortest path trees, and the places where they actually do go is a very small number of places, and it's very simple, and it has a very simple scaling. So this, for example, is a picture of the outgoing scenic transit traffic, and we're actually following the bits, and it kind of couldn't be simpler, right? There's 4 ISP routers, there are 6 next hops for the 4 downstream transits, and none of them are used twice. And then after the transit, it goes off into the internet. So this is, such simple linear flow. It's really easy to analyze this. It's really easy to construct pictures of it. So if we could somehow leverage this to get a view of the traffic world, we'd have a pretty tractable scaling. So that's not hard. First thing to observe is if you've got some NetFlow data, the stuff that's sitting over there on the left, it's got source destination address and it's got some volume of data. It says at some time A sent 1460 bytes to E. If you've got the topology that's over on the right, then you know the only way that A could get to E was to go A to C and then C to D and then D to E. And you know that the 1460 bytes went across each one of those links. So you can figure out what the link capacities are due to that NetFlow traffic by just adding the 1460 to every link in the path. Similarly for the second NetFlow record, adding the B to F. You do this for every NetFlow record that you've got. If you've got the current paths, if you've got the current topology, just take your data and distribute it across the path. What that's saying is if you've got topology measurement, topology data, you can take any point measurement and turn it into a path measurement. They're the same thing. And so you can take your local measured view of the data and extend it off to as far as you can extend a path, completely across the internet if you can get a BGP path to the final destination. So this isn't a new idea. If you went to Thomas Telkamp's tutorial, it's the basis of these automatic appliances that compute flow matrices for you. That's why they need the BGP data. If you're doing things this way, it's not really critical where you measure because any measurement you take applies to every segment in the path. It may be hard to get a path depending on where you measure because a lot of the routing isn't invertible. For example, if you measure BGP at an ingress, you have no idea where the data came from. You know the upstream that gave it to you, but you don't know the upstream of that upstream. It's because BGP data, because it's basically a distance vector protocol, you don't have a map, you don't have a topology. And it's almost never the case that the data came from the place that you're sending it to. You can't take your outbound route and use it as a BGP inbound route. On IGPs, they're almost always invertible, with the exception of multipath and a lot of other funniness. So if you've got an egress measurement from a customer, you know how that came across your IGP. If you've constructed traffic matrices, the bane of making them is if you got multiple measurements. You'd like to be sort of mindless in setting up your NetFlow infrastructure and just turn it on every router that will support it. But it's really easy to double count your packets if you're getting, say, both an ingress and an egress measurement, or you're measuring both input NetFlow and output NetFlow on an interface. You get this extra factor of 2, and traffic measurements accurate to within a factor of 2, or if you're measuring n places within a factor of n, are kind of worthless. Nice thing about having routing is it puts a total order on your traffic. You know which is the first measurement point that would see the traffic, which is the second, which is the third, and you can make sure that you only count it on the first and use all of the downstreams just to validate that first and check the first input measurement. So there isn't, if you're using topology, there isn't an issue with multiple measurements. You can really be pretty brainless in deploying your infrastructure. And unlike the tomogravity and other techniques that try to convert edge measurements back into what's happening in the center of your network, that require 100% data before they'll give you an answer, whatever data you give this technique, it can give you a picture of. Right? It's just taking individual flow records and distributing them across the topology. So if you've got one hotspot, one provider, one customer, and you really want to see what's happening with their traffic, great, measure that traffic, feed it through your topology, and you get a picture of it. So you start getting a return right away, start getting information right away, and as you deploy more measurement infrastructure, you just get a more complete picture. But you always get useful information out of it. Other issue is, how do you deploy a measurement infrastructure? Do you have to spend as much time babysitting the measurement infrastructure as you do babysitting your customers and their routes and their transits? And the answer is no. At least if you can leverage routing, all of the information that you need to configure the measurement infrastructure is already in the routing. Basically, you need to know what's a customer. How do I map a prefix into a customer, a peer, a transit, a bogon? That's already in your routing. You have to know where your connection to the outside world is, and you have to know where that connects into your internal infrastructure. Well, outside world connections are all in BGP. The next hops are all related to things that are in your IGP. You can glue them together and pretty much make a picture of the whole world of interconnections just by mining through your routing. So that's the two observations behind this route flow fusion. It says the right way to deal with flow data is to take the NetFlow data, don't try and analyze it into something like a traffic matrix, because then you're presupposing a question that'll reduce the volume of data, but it also reduces the number of questions that you can ask of that data, and it reduces the number of questions you can ask astronomically. Instead, you're a lot better off if you keep the raw NetFlow data together, you keep raw routing data at the same time, and when questions are asked, you fuse those two pieces of data together. Go through the flow data to get the prefixes, feed that through the routing data to get the path, and then accumulate the traffic along those paths. It's cheap to do that because you can take advantage of the simplicity that the routing introduces on the data, the fact that most paths go on simple shortest path trees. You do some caching, you can take advantage of the fact that same links are used for multiple different flows. And basically, you're doing a lazy computation of the flows driven by the questions. You're doing on-demand computation based on what the questions are. And you get this nice aggregate data rate and traffic volume across your infrastructure. So here's a picture of doing that. This is exactly the same data as that scenic traffic matrix. It's basically another picture of that traffic matrix, but it's showing you a little bit more. The way you draw this picture is you spread all of the flow data, this 24 hours of flow data, I don't know, about 50 gigabytes, I think. Spread it across the topology. That gives you loadings on a lot of paths. You go through all those paths with a threshold, and any path that's carrying less than the threshold amount, in this case it was any path that's carrying 1% of the traffic, you throw it away. And so look at this as your data is this big bushy tree with lots of leaves and blossoms and all sorts of growth on it, and you can't really see the structure of the tree. So what you do is from the outside you start trimming it back in until you can see the main branches in the trunk, because that's all you really care about to get a large scale sense of what's going on in the network. All the data goes, in all the pictures I'm going to show, the data flows left to right. So customers are on the left in this picture, internet's on the right, the transits are about in the middle. And computing this picture took no manual input other than you need to know the communities in the BGP data that identify customers and transits. And it took exactly the same amount of time as generating the traffic matrix. Each of them took about 10 seconds. You can see more on this picture than you can see in the traffic matrix. You can see where the data is going downstream. First thing that jumped out at me was a third of the traffic here goes to residential providers. That's not terribly surprising. In the UC system alone, you've got a little over 1 million faculty and students. And if they're not on campus, they're home working back at a campus machine, and their home machine is hooked up to some residential provider. So you see the SBC DSL connections and the Comcast and the Roadrunner cable modem connections to haul them back to school. You can also see some other things. You can see that the Quest transit is basically used to get to SBC via Sprint. You can see that the Wiltel transit got pruned off because it's carrying less than 1% of the traffic. You can see that Cogent basically takes you to Canada. So that's a picture where you're just looking at traffic volumes. You add up the total number of bytes that are going down each path. But you're not restricted to just looking at traffic volumes. To look at traffic volumes, you distribute a scalar, the number of bytes, across the path. If you want to look at traffic rates, you distribute a vector across the path, where the vector is the traffic rate versus time that you get out of the NetFlow record. So this is a picture of doing that. This is looking at 20 minutes of NetFlow data. The thing that we originally noticed was going into UCLA, the traffic took a nosedive. It went down to about 20% of its nominal value, and then it came back, and then it took another nosedive a little bit later. If you look down at the bottom, that little sort of strip chart, that's the actual vectors that's being distributed. So that's the kilobits per second versus time. Full scale on that's, I think, about 30 megabits, and the full range of time is 20 minutes. And you can see the two traffic dives. Unlike a traffic matrix or a list, the sort of stuff that you get out of RRD, the interface stats, which you can fit into a pretty simple 2D picture, there's way, way more data here, right? You've got all of the data for all of time going to all of space, right? You can see everything that's going internally. The data that you're working on has got all of the traffic between all of the endpoints. If you're distributing rate vectors, then you've got that picture at any time. There's no way that you can draw a simple visualization of that. It's just too much information to put out. And so the real research and deployment issues are not so much getting the data, it's trying to get it into a useful form. What can you do so that you can, an operator, somebody who wants to ask questions of this, can ask the questions and get useful stuff out. This is one sort of fumbling attempt at doing it, turn the data into an SVG animation. So you draw this graph, you can click on any linker node, and what you see is the data versus time on that linker node will show up in the graph at the bottom. So that's a way of getting from a particular point in space to the behavior, the time behavior of that point. If you click any point on the time graph, you get a picture of what the traffic looked like in the global topology at that time. So right now, I clicked at the lowest point of that curve, and what I'm seeing is what the traffic was doing over everything that I'm looking at the time, where blue is links that are losing traffic, green is links that are gaining traffic, and black is links that aren't changing. So you can see at the time that UCLA was missing this traffic, everything was missing this traffic. Each of those, the second level in circles, each of those is a separate NetFlow monitor, right? We're monitoring all of the ISP links in Scenic, and we're seeing the same behavior on all the monitors and on all the peers. And there isn't actually, I clicked on a link that's the raw NetFlow monitor, so we're seeing the raw NetFlow data. This isn't an artifact of the analysis we're doing of the path distribution. It's really happening in the raw data. So another way of looking at this data is not looking at its temporal behavior, but looking at the correlation, the paths. An example of that is looking at a prefix anomaly. So start by clicking on the UC Berkeley data in that first picture. So a way that you explore the topology is double click on some node and you get a picture of just that node. So we can see that UC Berkeley this is inbound traffic. It's nicely split between Cogent and level 3, roughly half and half. We're bringing all the traffic in from Northern California POPs. Berkeley's in Northern California, so we're not backhauling stuff across the state. It's some fairly good engineering's been done there, meds or something else. But if you click on one of Berkeley's prefixes, it's got two main prefixes. You click on the 128.32 prefix to see just the traffic for it. So all of the other stuff gets grayed out, turns into a shadow, and just the inbound traffic for 128.32 ends up in black. And lo and behold, all of the 128.32 traffic is coming from level 3. In 24 hours, there was no 128.32 traffic coming from Cogent. Either there was no announcement going out that way, or it went out that way and got ignored. So there was some interesting asymmetry, and you can make yourself crazy going around clicking on different nodes and seeing how data goes through your network and goes through the internet. Because you're doing this lazy evaluation model, you're not structuring the data to answer any particular question. Pretty much when a question comes up, you can go in and answer it. So one interesting one recently was, do I have any customer traffic that goes from Cogent to level 3 or from level 3 to Cogent? Because if I do, it's not going to work. And so it's easy to query the data to say, show me all the traffic where the AS path includes 174 and 3356. And this is a picture of that traffic. Turned out 100% of the traffic, which wasn't a lot, 27 megabytes, went to Schlund in Germany. It was pretty well distributed over the Scenic sites. You see 4 of them there, and they're the usual suspects. They're the 4 biggest, but pretty much all the customers were sending down that path. So obviously this isn't going to work if Cogent level 3 deep here. It turned out that this particular traffic, a manual piece of configuration had been installed to force the Schlund traffic to this path because there was some monitoring gear there. And unfortunately it got, like any manual install, it got overlooked. So it was still there at the time we took this data, but we took this data in February, and that router was rebooted and this config went away long before there was any depeering event. But there's always stuff like this in any real network, right? You have to reach in and turn some knobs and do some stuff, and it's not hard to forget that you've done that. So this is a technique that with the real bits that are flowing through your network, you can pull out and analyze the implications of changes. Okay. So far we've gone through, you can do useful things with traffic data, and the scaling isn't first principles intractable. You don't have these n cubed or n factorial sort of scaling numbers that say don't even think about it. If you do this lazy evaluation and just push your flow data through your current routing data, the analysis is pretty tractable. But pretty tractable if you're talking about umpteen gigabytes worth of NetFlow data. NetFlow is really, really wordy. And if you're talking about umpteen gigabytes, it doesn't matter if it's an n log n analysis. The n is so frigging big, right? Gigabytes is going to be slow, and so for an operator, it's going to take an hour to put up the display. That's unworkable. So what can you do about that? Well, you can do lots of tuning in NetFlow, but they all cost you. You can aggregate the data by prefix, you can aggregate it by AS, but when you do that, you can no longer see the parts of the topology that made up that aggregate. You're losing some detail. You can make any particular NetFlow record cover more of time, so you can increase the active or inactive timeouts so that particular records are covering more than 5 minutes or 30 minutes, but now you lose a lot of temporal accuracy. You can't see where events are in time, like you couldn't see those 2-minute outages because, or they turn into little tiny blips rather than big dives. Or you can sample the data. So decimated only take 1 out of every 1,000 packets that go through, and now you're losing both topological and temporal accuracy. Core problem, the reason why NetFlow is so wordy is because its model of the data, the way that it's representing the data, bears absolutely no resemblance to the data. And whenever there's a big mismatch between model and data, you end up with a representation that's really wordy. So this silly picture over on the right, the black line is what typical flow data is doing. It's always going down or going up. It's never staying the same. That stair-step thing is how NetFlow would have to represent the data, because NetFlow is what's called a piecewise constant approximation. It gives you the average data value in some time interval. And so what you see is the flat blue lines, flat horizontal blue lines, are the NetFlow representation of that data. You can see that it's never very close to the data, and if you push the time interval out, if you make the active time longer so that you reduce the volume of the data, then the NetFlow gets further and further away from the data, which is why you're always worried in NetFlow about, are you representing the average, are you representing the max, because the data doesn't give you a good picture, the NetFlow doesn't give you a good picture of the underlying data, and the NetFlow values are very far away from the max. They're only going to give you the average at some particular time. The red line there is 2 least squares line segments that are fit to the black data. And you can barely see them because they're pretty close to the data. There's a bunch of theoretical work that says if you've got data that is not constant, that's got any kind of trend in it, doing linear segmentations is going to be way, way better in terms of data representation than a piecewise constant approximation. Now, that's not intuitively obvious, right, because it takes more parameters to describe a line than it does to describe a constant. NetFlow data's got a time and a level, an average. That's 2 parameters per observation. A line's got at least 3. It's got a time, a level, and a slope. So it's going to be 30% more data per line segment. What you're hoping is the line segments fit your raw data well enough so there's many fewer of them. And so that 30% additional cost, you eventually amortize it over many, many fewer observations. Figuring out how to do those line segments also seems like a really hard problem. Like there's a lot of different ways to draw pairs of lines across some set of data, n squared different ways if you've got n data points. It turns out there's this really cool n log n algorithm done by a guy who's now at UC Riverside, Iamon Keogh, that'll give you a nearly optimal segmentation of the data for almost 0 cost. All of the time will be spent reading in the data and essentially zip and segmenting it. And it works really well on the traffic data. We find that if you're doing segmentation using something similar to Keogh's algorithm, you can do about 16 bytes per prefix pair per hour and get a very good representation of the NetFlow data. And I'm over. So here's a picture of that. This is 10 hours of NetFlow data. It was 500 megabytes. It had been prefix aggregated and sampled up the wazoo. The blue line drawn through there is the linear least square segmentation, Keogh's algorithm. It takes 64 bytes, so that's a factor of 10 million compression. You can see it fits the data pretty well. In the places where it doesn't fit, those little ripples in the data, those are all artifacts of NetFlow. If you look at them, they're all at 5 minutes or 30-minute intervals, and they have to do with the NetFlow cache timeout. NetFlow makes it look like you get a lot of data whenever the cache times out, because that's when the values are flushed, and then there's a long dead period while new things are coming in and populating the cache. So in all NetFlow data, you get some ripples. This gets rid of all of that junk, shows you the real data, and at fairly fabulous compression. Other issue, so you can get the data volume down, but you still got zillions of prefixes, seeing like 500,000 an hour. This is almost entirely one of Microsoft's gifts to the internet. All of those prefixes are various viruses that are probing for new Windows machines to infect. They look like just a random cosmic ray background. They're uniformly distributed across the internet. There's no information in them. If you want to analyze what's going on, you'd mostly like to get rid of them. There are general statistical techniques to do that. Nick Duffield at AT&T Research has done a wonderful algorithm called priority sampling that lets you trim off the tail of a large data set and still get something that you can analyze, where you can analyze aggregates and components of it. But since we've got topological data, you can actually do a lot better than that by using the topological data to aggregate. And the model for that is a lot like the inverse of drawing those graphs. You start out at the edge, you say, well, I've got all of these addresses, which is some host in China or Romania that's busy probing me, trying to infect my Windows machines. It's a very low bit rate because some residential host is rate limited. I can walk up the graph from that host towards me, and I've got some threshold where I say, okay, if it's below 300 kilobits per second, it's virus traffic. It's just this background, Microsoft virus background was the label on this guy. You walk up the graph till you hit a node where the aggregate traffic is more than 300 kilobits. And at that point, you aggregate the whole tree, all of these blue guys, into one node, and you say, okay, this is the virus background that's coming in at this node. And these trees tend to be pretty large. It's not just the 8 nodes that are shown here, but the place where you get above threshold, you've usually aggregated a few hundred nodes. And you're doing this all over your topology. So you're keeping the places in the global internet topology where the virus traffic gets big. You can still find that, hey, China is sending me most of my virus traffic, but you can't figure out which particular prefix in China is doing it. End result of that, if you go to a linear least square segmentation, you do these more efficient line segments, and you're aggregating all these junk prefixes so that you don't have 500,000 of them. You're doing segmentation on larger aggregates. You get some really nice data volumes. You turn those gigabytes worth of NetFlow down into kilobytes. It's about 200 kilobytes per hour per gigabit per second of NetFlow bandwidth that you're looking at. And that means that you can fit, if you're monitoring a gig ether, you can fit an entire year's worth of data on one disk. Which is not bad. So, conclusions. So, it works. Right? If you do this lazy demand-driven computation, you can get a detailed view of all of your behavior, stuff you need for operations, stuff you need for business. You don't need to babysit this thing. You hook it up and it dumps pictures out at you. You can get a usable amount of data for things like business purposes or forensic analysis. You can get a year's worth of data for a medium-sized ISP on a disk. And you can do it today. All the technology is pretty much available. We're really grateful to Randy Bush for initially pointing us in this direction, and we're deeply in debt to Daryl Newcomb of Scenic, who's been beta testing this and giving us data and finding our bugs and all that stuff. All done. Questions, if there's time?
Michael Sinatra, UC Berkeley. Just 2 quick comments on the 128.32 prefix traffic. I'm pretty sure that's intentional. I can't remember why. but we did do that for a reason.
Ah,
And the other interesting thing that you may not have noticed is that none of the traffic from Berkeley to Cogent goes through any of those 4 ISP routers that you were looking at. And that's due to a community string issue between us and Scenic that we just haven't bothered to resolve. So there are some lots of interesting things, and I just thought you might want to know about that.
cool. Thank you.
How do I feed you sorry, Randy Bush, IJ. How do I feed topology to you?
How do you feed to, the way I did these pictures was I went to Haobo and said, give me the topology, and he sucked it out of a Route Explorer. For just the BGP topology, you know, it's any kind of passive peer, use Zebra or something like that. There's the work that,
How about internal? Will you
so
read
it's-
LSAs?
yeah, so you want something that's generating your IGP. Yesterday I heard that Nick Feimster is extending his router configs validation stuff to handle IGP. So it seems like that would be a great source of IGP topology. And he's already got BGP, and that might be a way of getting the synthesized topology data.
Well, okay, so, but I can't just, you know, you don't have a IGP front end that I can just add to my IGP mesh. You pick up the LSAs and you've got the topology, for instance.
So there's two. So we would be delighted if you went and bought a Route Explorer to suck the topology out, and there is an XML RPC interface that'll suck the topology out. But you don't need to buy a Route Explorer to do this.
Okay, cool, thanks.